Okay, so this is the first machine learning algorithm that we are going to study. It is called linear regression. Here we are trying to map some physical pattern or some actual real life occurrences into a mathematical model. And here in our case, the mathematical model that we are going to use is going to be linear. Okay, so for an example, suppose we are studying two parameters or two features. These two parameters can be location of your house, or you can say the height of some height of an animal and the weight of an animal, right? And based on this, I'm taking an element and plotting their height and weight like this. Okay, so this distribution, how animals are distributed based on their heights and weight, is not known to us. There is no a book or a law by which we can understand, okay, this is the way they are distributed. So what we have is we have this data where we record their weights and heights and we plot them in two axes. We are just looking at these two parameters, right? So one way to do that, so the ultimate goal of machine learning is to predict any kind of a curve which can explain this behavior, and we know the equation of this curve so that we can put it into a computer and give it some outputs, right? So if so this distribution is can be anything, right? So if but this actual distribution or actual way in which this where data is coming from is not known, but we can use some mathematical technique based on this data to get a known model or a pattern or a quantifiable model out of it. Okay, so let's so in our case this curve can be anything, right? However complex, or it can be like a multi-dimensional curve where like this is not touching, only this portion is being taken into consideration, right? But here presently for our case we will be treating our model to be a straight line, right? So suppose whatever my data distribution it can be, I am trying to approximate this thing with a straight line, maybe this line or this line or this line or maybe like this line or any other line that we can think of. So based on this line, I want to map these two behaviors together, weight versus height. So in generally, we know the math y is equal to mx plus c is the equation of this line, right? We'll look into the details of it. Okay, so we just were kind of trying to figure out these two parameters m and c, because x is what will be our height and y w is weight, any one of these, right? So weight is equal to m times height plus some constant. So if we this thing somehow describes the location of all the points that you can find on any straight line. Okay, given the m and c, right? Let's look at it starts from the history of linear regression. Okay, right. So there was a guy named Francis Galton, and he was studying the relationship between parents and their children, right? So in particularly he was investigating the relationship between heights of fathers and their sons. Like some random thought came to his mind and he wanted to study the height of fathers and height of sons, right? So was there any relationship between these two heights? So we generally see that if the father is tall, the son is also tall or taller, and if the father is short, the son tends to be short, something like that. We see that in general life, right? So he wanted to study whether there was an actual relationship. Okay, so what he discovered was that a man's son tended to be roughly as tall as his father. Yeah, correct. So, however, Galton's breakthrough was that the son's height tended to be closer to the overall average height of all the people. Okay, so now what he observed was that in general case, if you take 100 people, so most of if the father is tall, their son is going to be tall. If the father is short, there is son is going to be short, right? The man's sons tended to be roughly as tall as his father, right? But in some special cases, what he found out that if the father was extremely tall enough, right? So maybe you'll see that in the, so for an example that he figured out, this is a basketball player, Shaquille O'Neal. Maybe if you follow basketball, you would know him, right? He is 7 feet 1 inch tall. He's taller than Amitabh Bachchan and he's very huge, right? 2.2 meters. Now, if Shakil has a son, the chances are he'll be pretty tall too. If he has a son, he's going to be pretty tall. This is what our observation and even the Dalton's observation gives us. Okay, but now Shaq himself is an anomaly, right? His himself, he's too tall that he does not belong to the general population. So if you now I am pretty sure that none of us have seen a guy this tall in our whole life. That amounts to 29 20 30 years of experience of data, right? Every visual we have seen, but we have not seen any real man who is this tall. Or if we have seen, there can be only at just one and two, right? If you compare them to all the people or normal people who we have seen, our parents, our friends, people we see on the road, so they are about what, between 5 to 6 feet mostly, right? So if yeah, we want to talk about the height of Shakil's son. What can you predict? Well, my bet will be like he'll be very tall. If he's 7 feet 1 inches, then I think he can go about 7.5, right? Because he's an athlete and all kinds of things we can bring into picture, right? But if this is what the same Delton also thought, that Shaquille has a son, then chances are he'll be pretty tall too. However, Shaq is such an anomaly that there is also a very good chance his son will not be as tall as Shaq. Right now, this Shaquille himself is an anomaly in my data set of heights of sons and fathers. That there are chances that he is not going to be tall as Shaquille. Right. So actually, it turns out that Shakil's son is pretty tall, 6 feet and 7 inches, still more than Amitabh Bachchan, but not nearly as tall as his dad. Right. So Shakil's son is tall, but he's not taller than his father. That I had assumed. Right, because he's 7 feet, I have 7.1. I thought his son is going to be uh, 7 feet 5. Right. So Galton called this phenomena regression, as in a father's son's height tends to regress or drift towards the mean average height, right? So this phenomena is called regression, where any property or any parameter tends to regress towards the average mean height, right? So if you see 10,000 people, if you pick any person, what will you say his height can be? So you cannot directly say he'll be 7 feet or 8 feet. You know, you have not seen that, right? So whatever the height is, your best guess is going to be the average of the whole population, right? So similarly, same thing he also observed. He noticed multiple taller fathers whose son was tall from the normal population, but he was not tall enough, right? He was not taller than their father themselves. So ultimately, sun's height regresses towards the mean or average height. That's why this kind of approach or this phenomenon is called regression. Okay, so any new property will tend to regress towards the mean position rather than going away from like. So if I give you some string of integers 2 4 6 8 10, and I ask you next, so you cannot tell 10,000. Okay, so we from the previous data we are observing that it is moving in certain fashion, it is remaining within certain range, right? So it is kind of drifting towards the mean always, it is not drifting away from the mean. Cool. So that's what the very detailed theory that Dalton discovered, right? So let's take an example in terms of mathematics, right? So I want to calculate regression between only two data points, right? Suppose I have this axis, maybe this is X and this is Y. I have 2 points, one is here, one is here, right? This is 1 point and this is my second point, right? I want to tell a regression or I want to just say, for example, I want to fit these a straight line which will explain this relationship, right? So I can just it's very common sense, I can just join these 2 points and I'll get a straight line which is passing exactly to these two points, right? So all we're trying to do is we calculate a regression line and we draw a line that's as close as to every dot as possible, right? So basically if we have 2 points, I have one person here, one person here, and I am studying their height, and their son's height relationship. So if I just have 2 points and I want to fit a line through this distribution. So this, suppose this is my whole distribution of 2 points. So how can I behave if I want to use linear regression over it? What will I do is I'll try to fit a line which is as close to this, maybe like this line, that line, or any line which is the closest to my data distribution. So if there are only 2 points, then this is the line passing through these 2 points is the closest, right? So for classic linear regression or least square method, you only measure the closeness in the up or down direction. So this least square method, we'll look at in the next slide, right? Suppose this is our general distribution of data, right? So my data is distributed like this. So what linear regression tries to do is that we want to try approximate this whole thing with a straight line. Maybe this line, or maybe this line is much better, or maybe this line explains it much better, right? So we want to find out the equation of the lines which explains this data distribution the best. Okay, and how are we deciding which line decides it to be best is by using simple mathematics, right? So y is equal to mx plus c, right? Mx plus c. So if I take any point in my data set like this, and my chosen line is this, right? So what I will do is I'll just take, okay, my model is saying the height should be, or this parameter value should be this one, right? At this particular x, this is x, right? So at x, suppose x1, my model says your equation will be y model, okay, whatever is there, xm, and this is the actual value which I observed. So my at xm, what is xy actual, right? So at a given x, I have two different values based on my model is giving me this height, my actual height is this much, so I have an error, right? So I take, if this is my line which I want to finalize, I'll take each and every point in my distribution and calculate the difference between the distance from the mean value or the value which my model is giving. So basically, I'll figure out the differences of the line from all the given points, and I'll try to minimize that difference, right? So let me yeah, so suppose if I take this line, then the distance of this line from all these data points should be minimum from any other line that I can choose. There, if I find such a line, I will say this is the line which best explains the distribution of this data. Okay, so our goal with the linear regression is to minimize the vertical distance between all the data points, right? So vertical distance means this is my x for any given x value. Suppose I take this point. This is my x value, say 7, it is showing 70, it is, let's say 73, right? At 73, the y value is y actual. Y actual means anything, the height that we observe from the real world, right? For this is the father side, then this is the son side. Okay, father side, and this is son side. Father's height, and this is son's height. Okay, and my model is giving me this value, right? This is the height that my model is saying, okay, you should have. I'm generalizing. Okay, so we will find all these vertical distances from all the data points, and we'll try to minimize this. So in determining the best line, we are attempting to minimize the distance between all the points and the distances to our line, right? So if I ask you, okay, you take a stick and place it at the center of this distribution, right? At the exact center where the line is almost at the minimum distance from all the points. So you cannot, so this line of course is very far from all the points, right? So this point, this point, this point, if you take, it's very far. If you take a line this side, this line also is very far. So to minimize the distances between each of these points, you need to place it at the center. Okay, you can kind of visualize it if okay, so there are a lot of different ways to minimize this. So there are different mathematical methods or simple common sense approaches that we can use to minimize this distance. Okay, so one of them is sum of squared errors, sum of absolute errors, right? So what kind of error I'm taking? I can minimize the absolute error, this minus this minus this. So whatever is coming, I can try to minimize it. Or I can take the mean squared error. I can take the error and square it, and then try to minimize the square. But all these methods have a general goal of minimizing this distance. So whatever distance parameter I take, direct absolute error or the square of the error or the root of the square of the mean error, whatever these three we discussed in the last class. So whatever measure we take, the ultimate goal is to minimize that parameter for all the data points. Okay, so for example, one of the most popular method is the least square methods, right? So here we have blue data points along x and y axis. So I have my data point, these 5 data points, this is the value. Now we want to fit a linear regression line over to it. Maybe let's suppose this line you want to fit. The question is, how do we decide which line is the best fitting one? So we'll use the least square method, which is fitted by minimizing the sum of squares of residuals. Okay, so basically it's nothing but I'll just measure the difference of each data point to this from this line in the vertical direction. That means I'm just the y value difference I'm checking. Okay, and I'll try to minimize this whole squared error, right? So basically, suppose for any value, my error squared error is going to be y actual minus y line or model or predicted, right? Whatever is there, you square it, right? This is for each data point, right? I have to so for this is for one point, this is my error for this point. For this point the error will be one second point, third point, fourth point, and fifth point. So what I need to sum it, summation from I is equal to 1 to 5 for all the values, right? I what is the actual for y1 actual minus y1 predicted, y2 actual minus y2 predicted, take the square. And now I have to minimize this whole thing, right? So this whole sum whatever is coming, I need to minimize this, right? So now for you can these are just 5 points, you can directly do it in copy in like 5 to 10 minutes, okay, if you have a calculator and everything, right? Ultimately but the actual data point can be very huge, around thousands or lakhs, and even it can go up to crores and millions, okay? So it's better to use a computer, do all this computation. We will just generally define whatever we want to do and which parameter I want to use, right? So luckily for us, for some people have already worked on Python machine learning, and especially in linear regression, where they have created a special library, right? And they have put all sorts of machine learning algorithms in that library, and it's open source and available for all of us to use freely. It's called scikit-learn. Okay, is sklearn library, in which I can find a linear regression model. I can just import it in my code, and I can define, okay, I want to use sum of squared residuals, and these are my x values, these are my y values, give me the equation of the line. So it will give me in just one line of code, right? So all this math we need to understand to know what is happening underneath any concept or any buzzword, right? uh, okay, so let's just go through this whole concept once again, right? So basically, for in a simple linear regression, we are trying to figure out this equation, right, where these two are my parameters, y and x1, right? So it can be height of our son, height of father, and this specific structure we are using because this our model is assumed to be a linear regression, and we are just trying to basically fit a line to our model, right? This is x, this is y, and this my data, it is distributed. I'm taking a general line, so I can call this general line as y is equal to mx plus c, right? Now I will, so suppose now I have these points. So I want to find the error function, right? So error function will be y actual minus y predicted, okay? So y actual is going to be a constant value, y predicted is what, m x actual, or whatever x is same, plus c, right? So right, this is my for one point. Now I will find this thing for all the points. It will look like this: y a 1 minus mx a1 minus c for one point, because it is a minus sign and this whole thing is in bracket, right? Next I have to take summation y a2 minus mx a2 minus c, right? And so on till the last data point that I have. So y a n minus mx a n minus c. So this whole summation I have to minimize, right? I have to minimize means I have to figure out such an value of m and c which best describes my data, okay? uh, so there are different ways of minimization, optimizing this particular equation. One of the most popular is gradient descent that we use over here. So just to get an intuition about gradient descent, try to do is, so this is the equation of general line. You think of how, suppose you are holding a stick, and there are a lot of tennis ball lying in the floor in some fashion. You want to align a stick in a way so that you can kind of be close to almost all the data, all the tennis balls. So what you can do is you can move your line in this. So maybe like if you take this the center, or maybe we can move the line in this particular angle, right? This angle theta we can move. So I can move like this, I can move like this, or like this, or like this, or like this, right? The second thing is I can this is my data point and this is my line. I can shift it in the y direction. Okay, so I can make this line, this line, this line, like this line. So these two parameters m and c corresponds to this tilting of the line theta and the height from the height or the offset or c, right? So but basically we will keep changing the position and rotation of my stick in all over the floor to find out which is the best location for my for my stick, right? So for this we have to actually perform a lot of simple mathematics, a lot of calculations we have to do. Okay, so all this is presently done by a library for us, but we need to know what's going on. It can be you can, anyone can ask you this question and you need to know what's going on. Okay, so now
Yeah,
some
I have a doubt here, Vinay sir.
yes, Anup.
Yeah. So once you call this dependent variable and independent variable, fine. So
Hmm.
how are the constants? What you told, the lines or the sticks?
Hmm.
How are these constants acting on the, like, once you plot the lines?
Hmm, hmm, hmm.
How are the what is the effect of the constant, and what is the effect of the coefficient once you plot the line?
Okay. So actually it is there in the next few slides, but just to quickly tell you.
Okay, sorry.
So this B1 B naught is so B naught is this value where it is passing my from the where y is equal to 0, right? So just you can figure out what is b by putting y is equal to 0. So 0 is equal to b naught plus b1 star x, right? b1 x1. So now it gives me b naught is equal to, sorry, it gives me x1 is equal to minus b naught by b. We have to figure out b1, yeah, right, sorry, maybe. Yeah, so if this is the line, then this length is b naught and this slope or this tan theta is equal to b1. So this is the general two relationships, right? So how tilted is the line, the how tilted is this line is told by this b1 constant, which is called the coefficient, right? So coefficient, it tells me what in per unit change in x1 how much y is changing, and b naught tells me what is the bias or what is the default offset, right? This b naught thing. Okay, when my x is 0, if I put my x1 is equal to 0, then y is equal to b naught. So when my x is 0 here, my y is going to be b naught, and when my y is equal to is 0, my x will be minus b naught by b1. So my x is going to be minus, when y is equal to 0, my x is going to be minus b naught by b1. So this point, right? Okay, so now this is called dependent variable. Why? Because we want to study this variable based on this x1 variable or multiple other variables in general. Now x1 or the vector x, or you can say x is called an independent variable because we want it, we are assuming that our dependent variable is effect is depending on these x1s to for its change, because we are studying y1, we want it as we assume that it depends on these two features. Like if I am studying the say performance of promotions, then it can depend on number of user clicks and number of recommendations that we made based on the promotions. Okay, like that. Okay, this thing is called a coefficient because it's attached with this x1 variable. This thing is the constant because it is not attached with anything, right? So in simple linear regression, suppose we are looking at a distribution of salary versus experience. So we assume salary to be dependent on experience, because generally if the experience is increasing, I should get more salary, right? Now suppose I want to fit a simple linear regression on this thing. How can I approach, right? So here my equation of line changes to this thing: salary is equal to b naught plus b1 times experience as a function of experience, right? Salary I'm getting as a function of experience, and here in our particular case this function is linear because it's a linear regression, and how it looks like mathematically is this structure. right? So I want to find the equation of this line, which is at the minimum distance from all these data points, right? So here b naught and b1. So if you put yeah, so b1 is this 30K, right? So I told you that b1 is this height. So basically it says when the experience is 0, what is the salary you are getting, right? So this is my data is saying at salary is equal to at experience is equal to 0, salary is equal to b naught. Okay, if you put it 0, this whole thing will become 0. So my salary is equal to b naught. That so it is my model is saying what it means in the real world is that, so when you are a fresher, when you join any company, or you when you get your first job, you will get this much of salary. It's fine only, right? This much you will get. Now next is what b1 is saying. So now if you put salary is equal to 0, right? If you put right here, if you put salary is equal to 0, it's b naught plus b1 times experience, right? So I get, I need to figure out b1 now. B1 is equal to minus b naught by x, whatever you have experience. Okay, so now this thing, now I want to study, suppose if I increase my experience now by just 1 year, what is the increase in salary I can expect? Salary is equal to b naught plus b1 into experience, right? So it says how valuable your experience is. So if b1 value is small, that means if you increase experience, your salary increase is very less, right? So your line looks like this. If b1 value is more, that means if you increase the salary by same amount, your salary will increase more, right? So this tilt in the line is given by the b1 parameter. So b1 parameter tells me if so here b1 is 10K from data we are getting, because we know. So in real world, I have all the x and y's to calculate b1 and b naught. Once we get this model, we can use new x values to figure out the y values. Okay, so here in this particular case, from the data we found out that the b1 value is 10K. Let me just remove all the once more. Yeah, so the red b1 b naught value is 30K thousand. So at zero, at just fresher level or zero level of experience, you will get a salary of 30K thousand, or a starting salary. With an increase of just 1 year increase, you can get you can expect to get an increase of 10K, right? So for b1 value is 10K, 10,000, right? So my equation looks like this: salary is equal to 30,000 plus 10,000. So it is what, 30K plus 10K multiplied by number of years you have worked, or y, or and whatever you can say, right? So if you want to figure out, okay, what is my salary, what should be my salary according to this model if I worked for 10 years? So my salary is going to be what, 30K plus 10 into 10, what is this, 130K, right? So your salary is going to be 1,30,000 per month after 10 years of experience, if you go by this trend. Now thing is called, okay, so is in this job there is not much growth, right? In Amazon the growth is like this, in Facebook the growth is like this, right? In normal IT companies the growth is like this. So this is what, when they are talking about growth, they calculate this metric. They try to figure out the equation of this line, right? So this is, so if you join a company who says, okay, this is the growth, in 1 year you will get 30,000 increment. In another company you will get in 2 years, in 1 year you will get 5,000 increment. So of course you will try to join the better company. Okay, so this is a simple linear regression when we use it to explain any distribution. Okay, it's a pretty good example. uh, so now what are ordinary least square? So basically this is the method that we are trying to find this line, equation of line, right? So I have this experience, I have salary, I have these data points, right? All these data points, and it's their distances from my line. So I will try to figure out this difference, y minus y hat. Y is actual, y hat, y dash, y prime, or y a, anything different, or the other term is always the predicted one, right? Prediction. One is actual, one is prediction. You keep this in mind. We have to minimize this whole thing. Okay, okay. So this is it, what we had to discuss in the theory part of linear regression. Right now, next we look at how to use scikit-learn to perform this in actual. Okay, so I am stopping this meeting. I'll start a new meeting like in just right now, and we'll see there. Okay, bye bye. Thanks.